There are a variety of plasticity mechanisms which allow networks of neurons to represent the statistics of the world. The most well-studied plasticity mechanism is synaptic plasticity, or Hebbian plasticity. But other plasticity mechanisms exist and operate in tandem. One example is intrinsic plasticity, where a neuron's excitability to input changes as a function of its own past activity. Intrinsic plasticity, or IP, is typically modeled as a negative feedback loop that preserves a neuron's excitability despite its changing input. There's no consensus on which quantities IP regulates, for example, a neuron's firing rate, its internal calcium concentration, its spiking threshold, etc. There have been suggestions that IP plays important roles in circuit function, but its computational purpose is not fully understood. We show that IP allows a neural network to learn statistics about class-specific input gain. In MNIST, for example, different classes of digit have different gains, i.e., the sum of the pixels in an image. Digit 1 has the lowest overall luminance, digits 2 and 3 are similar, but a bit higher, and digit 0 is larger still. We propose a novel generative model that accounts for not only class features, but also class-specific variation in input gain, shown here. The solid curves are our generative model's fit to MNIST's gain data. We show that a specific form of IP can learn the expectation of those curves for each class. We derive, from first principles, a bipartite neural circuit that implements inference and learning for this model by combining specific forms of Hebbian plasticity and IP. The circuit is on the left, and the learning rules on the right. Our derivation yields a novel IP rule as a required component of unsupervised learning, given class-specific gain variations. The network's learned weights and excitabilities optimize the data likelihood under the generative model, at least locally. To test our derivation, we used MNIST as input to the network. The synaptic weights of the network learn different writing styles for each digit during training, panel B. The network also learns the average gain of each class of digit, panel C. The network's learned intensity differences improve classification performance, regardless of the number of labels used or the length of the training period, panel D. Our model makes novel and testable experimental predictions about the functional role of IP. Past IP work assumes that target excitability is a fixed value, usually shared across neurons, but our model proposes a link between neural excitability and real-world statistics. It also provides a rationale for the dramatic variations in excitability across neurons, even within a local cortical circuit.